Welcome back, everybody. So I left you with the group bys, which is a new clause that we have. I told you what to do and what not to do with this. I had a few more slides in here. Yes, in my example with gamma, there was 2 grouping keys. This is how you have 2 grouping keys. You just you put the 2 grouping keys in the group by and in the select. And again, I repeat, it should be an automatic thought. The moment you put grouping keys in there, you should also put them in here, always, right? It doesn't obligate you to do it, but if you don't, that's going to be confusing. Because, for example, this is what happens. If you say, I'm grouping by century and captain, but I only put century here, that doesn't make any sense, right? I basically have the century 23, then 24 and 24, but I don't know which captain, and I have 2 values, but I don't know what they correspond to. So this is why you should always have the both of them. All of the grouping keys should also be in the projection. For whom does that make sense? Okay, everybody's following. And finally, I'm adding one more clause, but actually it's not really a new clause because it's just the where clause appearing under another name. It's the having clause. The having clause is basically a selection, just like the where clause. Except that the difference is that the having clause comes after the group by, and so that means that the having clause sees the effects of the group by. So in the having clause, you can filter by the aggregates. For example, you can say I'm filtering where there's strictly more than 2 records, count star strictly more than 2. I cannot do it in the where clause. Why? Because the where clause is before the group by. So this is why. I have no idea why they called it having and why they didn't also call it where, because in the more modern query languages where you can swap the clauses, they call it where. But in SQL, it's called having, right? So there is a different name if you do it after group by. Okay, so you see what happens here. I'm basically grouping by century. In here, I basically have the groups 23, 24. And I only want the groups for which I have strictly more than 2. Oh, I have 3 times 24. Sorry, I changed a little bit the data in order to make it more exciting. So this group with 24 is strictly more than 2, so it survives the filtering in here. And 23 doesn't survive because it's just 1. So only 24 survives, and then we only output it. We don't compute any aggregations here, but we learned that only the 24th century has strictly more than 2 records. Who is with me? Right? So think of it, the having clause, think of it as a where clause that's after the group by. That's really that easy. So now if I update my query plan, in these queries, we first filter because there might be a where clause before the group by, so we filter with the where clause. Then we group by, that's gamma. Then we filter again, but now that's after the group by, so that's having. And then we select with all the new names, and we might rename also what we want in the outputs. Or that's the tree vision. Again, it's a tree that doesn't have any branches, but it's still a tree, right? The trees can also have multiple branches in computer science. Multiple branches will come when we have the joins, actually. When we join table, there can be multiple of them. Okay, who is with me? Okay, so before I move on to something else, I remind you of the rules that I've already said and maybe a few more. When you aggregate the columns, give them names. If you don't give them names, PostgreSQL will, but you might not like the names because it will just make up some things. Sometimes it reuses the old names, sometimes it creates new names. It's always a good idea to rename when you aggregate, right? Just like I did. I think whenever I had a count, I have as, you see, count as C, so you give it a name. I think if you don't give it a name, it's going to call it count, the column, right? But then you cannot really assume anything. So always rename aggregated columns. Number 2, I've told you already several times, always include all the grouping keys in the projected outputs, always. The third one is usually, when you group, you should also aggregate at least one thing. Why would you not aggregate anything and only just group by without anything else? Well, that would be for duplicate elimination. You're only interested in the groups and what characterizes the group. Who sees that it's the same thing as select distinct? Right? So group by on a few grouping keys without aggregating anything is the same thing as select distinct. You're just looking at the distinct values, all one per group. I actually did that right here to not aggregate anything, but I had a having clause. That's the reason. Here I had a having clause. If you don't have a having clause, if I hide, yeah, there you go. If you don't have the having clause, who agrees that this is the same thing as select distinct sentry? Right? Very good. You see it. That's the same thing as select distinct sentry. So this is why usually you should do select distinct instead of group by if this is what you want to do. Avoid aggregating grouping columns. For example, in here, what if you say select sentry and then count of sentry or sum of sentry? That doesn't make much sense, right? So usually you really have a strict separation between the grouping columns and the non-grouping columns. The grouping columns, you put them in the group by and in the select, and the non-grouping columns, you choose some of them to aggregate in the select, but do not mix the two categories. Do not aggregate grouping keys. That doesn't make much sense. And finally, do not use having alone. Do not put having if you don't have a group by. That's exactly the same thing as not using limit and offset if you don't have an order by, right? They are really supposed to be used together. So having is really supposed to be used with a group by. Okay? For whom are these rules clear? Okay? Since we are done, I'm going to move on to joining. But before that, I would like to recap the order of the clauses that we know. Select, from, where, group by, having, order by, limit, offset. They're all optional except select, but always in that order. Okay? Always in that order. Select, from, where, group by, having, order by, limit, offset. That's really a list you should learn by heart. When you fall asleep, you know, in your bed in the evening, just recite it to fall asleep, right? So select, from, where, group by, having, order, limit, offsets. Okay, who is ready for the next part? Joining? Okay, then I'm going to continue. You already know what it is because we did the theory, right? We did the relational algebra of this. We saw that the joins involved multiple tables, so that's something new because until now we only had one. I see a question on Zoom actually.
Avoid aggregating grouping columns. This means not having both century and age in both group by clause, right?
Yes, if you aggregate by age, I think you're referring to a slide where I had, yes, this one. What I mean is that you shouldn't have group by century age and then century max age. That doesn't make any sense, right? So the ones that you aggregate here, they should not be in the group by. That should be the others that are non-grouping, right? So you have a strict separation between the grouping keys that are here and the others that you may or may not aggregate that are only in the select clause. That's what I mean. Does it answer your question? Yes. Awesome. Okay. So now multiple tables. So it's becoming very interesting. So we can do a lot of things with multiple tables. We can compute the Cartesian products. We can compute joins. So you saw the natural join, the theta join, and so on and so on. We'll see them again anyway, because I'm going to explain the query. So in case that wasn't clear last time, then you have another chance of understanding them. What you see on this screen is a natural join. It's a natural join. A natural join is done on two tables that have some columns in common, that have the same name and types. For example, B integer is in both R and S. And so it means that we try to combine the records in R with the records in S that match on the column B, right? So we look at the column they have in common and we match. So it means this B1 and this B1 will match, and this B2 and this B2 will match, and we get this, right? Who is with me? That is a natural join. That is super important in databases, the joins. And I don't know why I left this slide, because that slide was only, actually only meant as I don't know what I did in here. That's not the Cartesian product, because there would be 6 of them. 1, B. I think it's probably a theta join, and I didn't put the predicates. Maybe we can reverse engineer the predicates that I meant in here. So I have 1, E3. Yeah, just ignore that slide. I think I just forgot to put some predicate in there to basically say what I'm filtering on. So I'll try to find the predicate, or maybe you managed to find the predicate that I used in here. I should have put it in here. Anyway, let's look at the queries, because this is what we're interested in right now. I'll start with the Cartesian product, the one that can crash your machine at the exam and that you need to be careful about. How do you do a Cartesian product? Well, you just put multiple tables in the from clause, comma separated. So if I say select star from persons, comma spaceships, how many records will I get in my output tables? 6, absolutely, on Zoom. Yeah, absolutely. 2 times 3. Every combination, that is the Cartesian product. It's also known as cross-join. That's just another name for the Cartesian product, cross-join. Cross because it's across the Cartesian product. It's like a multiplication sign. And because it's also called a cross-join, PostgreSQL also allows you to say cross-join. It's the same. You can put a comma, you can put cross-join, it's all the same, right? That is the Cartesian product. Again, be very careful. That's how you crash your machine if your tables are too big. Next. How could we build a theta join that joins these 2 tables on, you probably guessed where, the last name on the left and the captain on the right, right? I would like the last name on the left to match the captain name on the right. Can you find any way to do it in SQL without introducing anything new, only with things that I've shown you so far? Can you write a SQL query that does that? A theta join on these 2 tables. Maybe I can tell you as a reminder that we had an equality last week that says that the theta join is the same thing as a Cartesian product followed by a selection. Who remembers that? Who doesn't remember that? It's okay not to remember, right? Okay, then we see it again. Learning is also repetition. You see it multiple times, and then after a while, it just reminds. So since a theta join is the same thing as a Cartesian product followed by a selection, I can do a Cartesian product. And how do I do a selection in SQL? With which clause? Select. Any other ideas? So somebody says select. What do you say? Where? Any other ideas? So let's vote. Who says select? Who says where? We have a majority from where. Oh, you change your mind too. So it is indeed the where clause. It is indeed the where clause. That's the trap I warned you about, right? I told you, be careful. The select clause is in fact projecting and renaming. And the selection is in the where clause. So we can use a where clause. So I just write my Cartesian product with my 2 tables, persons and spaceships, followed by sigma. That is my where clause right here. And I'm getting my theta join. Only these 2 because I'm also projecting on just century and warp. Do you see what happened here? I had Kirk matched with this one and this one. So that gives me century 23 with warp 5 and 4. That gives me this with Kirk. Then I have what other match? So Picard, Crusher doesn't match. So Picard. That gives me 24, 9.2. And then I have Janeway with 24, 9. Yeah, the 10 is the asymptote for that. So 9.975 in here, right? So that is a theta joint. Who agrees? Right, that's a Cartesian product followed by a selection. Okay? So that's the good news, right? We can actually already use what we know of SQL to do it. Now, here's my next question for you. I told you Cartesian product is very expensive. So imagine that I have a table with 1 million records on the left and a table with 1 million records on the right. And I'm writing this query. Who here thinks it's going to crash the machine? See one raised hand. Any other raised hands? Yes, 2, 2.5. Okay. Who thinks it's not going to crash the machine? Does anybody think on Zoom? One person on Zoom thinks it's not going to crash the machine. 2 people on Zoom. More people think it's not going to crash the machine? 3, 4, also 4? Okay, so the answer is it's not going to crash the machine. And this is the power of data independence. This is what I told you about and all these mini theorems that we saw. It's that even though it's a Cartesian product followed by a selection, which sounds very scary because at first sight you would have a Cartesian product of millions and millions, so it's trillions of records. But PostgreSQL has an optimizer that is detecting here. It looks, oh, that looks like a theta join. So it's going to rewrite the query plan and replace the Cartesian product and the selection with a theta join. And a theta join is actually can be implemented in a much better way. We can use, just for those who know who that is, you can use hash tables and so on. So we know how to efficiently join a table with 1 million records with another table that has 1 million records with a join that involves an equality predicate. We know how to do it very efficiently, so this is not going to crash the machine. Although maybe adding a limit 10 could be helpful just to not overload the notebook, but it's perfectly fine. Who understands this, that it doesn't crash the computer? Okay. It's again because even though you write the query in this way, PostgreSQL is smart enough to rewrite it and execute it in a way that doesn't crash the machine. That's probably some of the strongest benefits of using a system like this rather than writing it all in Python. Okay. But there are people who prefer to be explicit, and so you can also do it in this way. It's exactly the same thing. It's absolutely the same thing. We just explicitly say that it's a theta join. So we say we join this with this, and that's the predicate of my theta join. That's the subscript that I put after the sign, the cross with the 2 vertical bars. So that would be the predicate of my theta join. This is the same thing as this, exactly the same thing. It doesn't matter which one you write. PostgreSQL is going to anyway rewrite it in this way, and it's going to be able to compute it as a theta join. Okay. By the way, this is called the table expression, right? When you have in the from clause, so until now we just had the name of a table, but in the from clause you can have much more complex things than just the name of a table. So in that case, the full join, right? Just as a word of warning, table expression in the PostgreSQL documentation has another meaning, so don't be surprised by this, right? That what I call a table expression is just what you have here in the from clause, so something that returns a table. You can make computations, and it gives you a table. Okay, so that's the theta join. Now, this is also the same. It's just because by default, we do an inner join, right? So an inner join is exactly this. It just takes the records on the left that match the record on the right. And the records that do not have any match are not in the output. Do you see the records that do not have any match here? There is one record that doesn't have a match. Can you spot it? And raise your hand when you see it. You see it? You see it? You see it? Yeah, so where is it? Crusher, exactly. Crusher is not a captain, so it doesn't have a match. And that's why we called an inner join, that you only output those that match. So you're seeing here 3 queries that are exactly the same. Inner join is the same as join is the same as this. It doesn't matter if you do this or this or this, right? If you just say join, it is an inner join, always assumes to be an inner join. I did the same, but instead of century and warp, I just put select star. So now I have everything. So now you see the whole join where you have Kirk that has 2 matches. This Kirk has 2 matches. Crusher doesn't appear here. Picard with Picard, and Janeway with Janeway in here. Okay. Now, of course, so this is the predicate that doesn't have any match. And you might remember that in the relational algebra, we said that there is a way to join and keep the records that don't have a match. So we might want to include Beverly Crusher in the results of the final results. And because it doesn't have a match, we just put nulls on the other side, right? Do you remember that? That's called a left outer join, because we want to include the records on the left that don't have a match. It's simple. All I have to say is left outer join, or left join is going to work too. Left outer join or left join. On person's name equals spaceship captain name. And the only difference with the inner join is now that Beverly Crusher appears in the results, even though there is no match. And we just put nulls in here because there are no matches. Who is with me? Right? That is called the left outer join. Then there's the right outer join that does the same thing on the other side, right? So in that case, I just removed Picard on the persons to make sure that it doesn't have a match. And then it's the opposite, right? So there's no Picard here anymore. So I have Picard here, the record on the right that doesn't have a match. And I just put nulls all over the place. And finally, I have the full outer join if I want to include everything from the left and from the right, all the records that don't have a match. So now I just include them all, right? So it means I have 4 categories: inner join, left outer join, right outer join, and full outer join. These are all the combinations of including or excluding the records on the left or on the right that have a match. Okay? So that's it. So you see, inner join, left outer join, right outer join, full outer join. That would be if you want to spell the whole names of the joins. So far, so good. Everybody with me? So inner, left outer, right outer, or outer. Now, do you remember that in all the queries I've shown you, the predicate was explicitly formulated on all these cases: inner, left outer, right outer, full outer. In all cases, I had an on with a predicate. So these were all theta joins, all of them, right? You see on every slide I have on, it's everywhere, always on. Now, do you remember what it's called? I just said a few minutes ago, what is it called if instead of specifying the predicate, I just pick the columns that have the same name? Do you remember how it's called? A natural join, exactly, a natural join. So for the natural join, it's even simpler. I remove the on blah, 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 blah. I completely remove the on and I write natural. That's it. Instead of on, I just say natural. Natural basically says whatever columns have the same name, they must match. Natural works with everything. You have natural inner join, natural left outer join, natural right outer join, natural full outer join. They all work. So you can combine everything with what you want. On the one side, you can use the on for a theta join, or you can use natural. And on the other side, you can say if you want inner, left outer, right outer, full outer. That's already 8 combinations so far, right, that we have. Who is still with me? Right? And so if I click, we'll see the results of that. So here, what are the attributes that are the same? because it's a natural join? Well, we have last name, that is the only attribute that exists on both sides. So it's a natural join, it's going to match this. Crusher doesn't have a match, but it's a full outer join, so it's still in the results with nulls. Picard doesn't have a match, but it's a full outer join, so it still appears in the results with null. And Janeway, right? Who agrees with this output? Right, so that's a natural full outer join. Do you have a question? So the question is, I'm repeating for the people on Zoom, what if you have a natural inner join with no attribute in common? So the first answer and the first thought that you should have is, do not do it, right? That shouldn't be something that you should do. If you have a natural join, normally you do it when there are columns that match. Now, we could check what PostgreSQL does. In theory, if you think like a mathematician, what is a natural join? It's basically a Cartesian product followed by a selection such that all columns match. Now, if you have your mathematician hat, that's called a universal quantification. For all columns, it must match. And it turns out that as a mathematician, when you quantify on the empty set, meaning for all elements in the empty set, this happens, it's always true. That's just a mathematical convention because it makes a lot of things smooth and logical and natural in theorems. So what it means, if you think like a mathematician like that, it means that if you don't have any columns in common, then the filter is going to let everything go through because you're quantifying on the empty set. So it means that a natural join where you don't have any columns in common is the Cartesian product, basically, if it's an inner join. Right. Okay. Does it make sense? Yeah. So that's a very good question. It's great to think about that. But in practice, if you work in a company and you write queries, then you shouldn't. You shouldn't have a natural join that does it if there's no columns in common. Okay. Any other questions? All right. Just checking the time. And speaking of natural inner joins, it's a very good transition to what I have to say here. It is risky. So first, it's risky because you might have no columns in common, but it is also risky because you might accidentally have columns in common, right? Unintended. Imagine that instead of having Sentry here, I just put C because I'm lazy and I just figured out that name, right? And instead of code here, I put C as well. Do you see that these two columns have the same name? And so a natural join is also going to make them match. But that's probably not your intention. You probably did not intend to match the Sentry with the code, right? So that's a bit dangerous. If you use a natural join, you should really do it if you see the schema and you're sure that the columns that match your intention, right? So in that case, how many records in the output of that? Who agrees it's empty? Right? It's never going to match because that would imply that we match here and here, but they never match. It has nothing to do the one with the other. So we're going to have nothing in the output. But again, this is not intended. That is accidental. There just happens to be more columns that had their names in common, right? So for this, we have a third way. So the first way was on, that's a theta join. The second way was natural, that's a natural join. And we have a third way where you explicitly say which columns you want to match, but you don't need to write it as an equality predicate and something. That is the using keyword, using. By saying using, you specifically say it's the last name that I want to match, right? So that's last name here matches here, but it's not matching anything else. Even if there had been C here and there, that would still have only matched last name. Who is with me? Right? So we have a total of 12 different ways, 3 times 4, to write this. 3, because you can use on with a predicate, you can use natural, or you can use using, one of the 3. times 4, because you can say inner join, left outer join, right outer join, and full outer join. So that's 12 possibilities. It's like the restaurant when you combine the starters with the entrees and the desserts, right? Okay, so that's the using clause, using last name. Using, that would have been equivalent to saying full outer join on persons.last name equals spaceships.last name, and then we project one of the two away. We remove one of the two columns. Who agrees? Right. Who would feel comfortable now writing joining queries? Right. So I recommend you do it. Take the Jupyter notebooks and start writing queries in order to make yourself familiar. Right. There's only these 12 ways.
Question?
Yes.
Could you please explain what happens when two columns have matching names in a natural inner join?
In a natural outer join.
Inner join.
Oh, inner join. Yep. Yes, natural. Yeah. All right. So this one I assume. So this is a natural inner join, as you're asking on Zoom, and we have the matching names. What that means is you're putting together the records that exactly match on these columns. So here, for example, you take this record right here, Kirk 23, and you're looking here, is there Kirk 23? No, nowhere, so that doesn't match. And you do it for all possibilities. You match these pairs with these pairs, and you only keep those that match. Does that make sense? Yeah. In that case, that was unintentional because you didn't intend to actually match them, but there are cases where it's not accidental, where it actually makes sense to have multiple columns that match in a natural inner join, right? So that sometimes makes sense. And then you just match all of these columns. They all must have the same values to have an output record. All right, awesome. Don't hesitate to ask even more questions. That's really what I'm here for. Okay. Yes. What if we do joins like this? This is another thing that can happen. We have a join, not a natural one, because that couldn't happen with a natural one, but let's say with using and so on, we might have the same column that appears on both sides, and it's not in using. Do you see that it means it's going to appear twice in the results as two different columns? But we can't have that in the relational model because we can't have twice the same column. So what we need to do, that's why I put them in red. What we need to do in that case is to rename them, right? So we say the one that comes from the left, so we use the name of the table dot name to mean this one, we rename it as p name. And the one that comes from the right, we rename it as S name, right? And we put in there, right? So you should not let twice the same name in the output. If you do, that's going to be okay, but then what PostgreSQL is going to do is going to say persons.name. You will explicitly see persons.name as the name of the column, and spaceships.name in order to make sure that it's different names, right? But to be in control, it's better to give the names you want, because then you control everything and you choose the names you want. For whom is that clear? Right, very good. And that's not new because that's us, that's the renaming, and that's something we've already seen before. Okay. Now, speaking of us, you can rename a column or give a name to a column with us. Well, you can do the same with tables. So in the from clause, after a table like persons, you can add as p, the same syntax that you have for attributes. You just give it the name p, right? And then spaceships as s, you give it the name s. And these names, p and s, then you can use them in here, right? You can say p.name and s.name right here, okay? So it's exactly the same mechanism. You can rename attribute, and you can also rename the tables here. You won't see it in the output, but that allows you to write shorter queries in here. But that's the same as here. Okay. But there is, oh yes, here I want to say do you remember that as is optional? I think I briefly mentioned that in here, you can just remove the as and it will work too, right? That's an optional keyword, but still I recommend that you always put it explicitly. That can avoid a few problems or ambiguities in the query. So it's optional. This one is also optional. So you can also say persons P, spaceships S. I think that here, most people do use the alias. In the from clause, there are a lot of people that don't put the as. There's a lot of people who just say persons P, spaceships S, mostly because they think a bit like in Java or C++. It gives the impression that you're basically, let P be a person, let S be a spaceships. So this is why some people omit the as keywords. Right. If you want to be totally safe, just always put the as keyword, and then you will avoid maybe some syntax errors at a few corner cases. So this is the same. There is one thing where you have no other choice but give names to the tables. That's when you join a table with itself. How does that make sense? Well, imagine here you have a table spaceships, and every spaceship has a successor. There's the original spaceship, then there's Enterprise A, then Enterprise B, Enterprise C, and so on. So every time you have a successor, and here I'm bringing in concepts that we've seen. The code here is a primary key for that table, and this is a foreign key referencing the same table via its primary key. Do you see this? Here we have Enterprise A. Its successor is Enterprise B, which references this record. So it's a foreign key on the same table, back to itself. Think of genealogy, a table of people, and then you have the parents, the children, and so on, right? Also referencing the same table persons, right? It's basically a graph. Well, in that case, if you want to do the join, you can write it like this, like spaceships join spaceships. But then you have a problem of ambiguity, because here, if you don't rename them, you cannot distinguish between the two because they have the same name. So for this reason, you say, okay, this one I call S1 and this one I call S2, right? And that allows me to specify my theta join because I'm using on here, on S2.code equals S1.successor. It means that S1 is the previous one and S2 is the next one. And I match in this way. Plus S1.name, I call it former, and S2.name, I call it next. Who is with me? Okay, so this is a case where you don't have any other choice but rename them. You have to rename them because otherwise you just have two tables with the same name. Okay, that's already a bit advanced to do these kind of things, right? To join a table with itself, but it can be a good thing to play with. And that's what you get, right? You basically see that corresponds to the structure here, but enterprise is followed by enterprise A by B, B by C, and C by D, right?
Could you explain again what happens to the data types when merging, when they are different specifically?
When merging which? When merging what?
Data types. I think someone asks to explain again what happens when you do aggregation, I assume, to different data types.
Aggregation of data types. Yes, we could come back. That's what you looked at during the break, right? So maybe we still have a few minutes. So you're probably referring to the question on string ag, where you had incoming strings, and then you aggregate them, and you were asking about the data type of the output column. Is that what you refer to?
Yes, exactly.
Yes. So Martin looked at it during the break. There is a page on the PostgreSQL documentation that has a beautiful list of all the aggregations and what they do. And basically what this documentation says is that whenever you aggregate strings, and that can be varchar with limited length or char and so on, the output will have the type text, unlimited. The same goes with binary values. When you use the limited, how is it called? Or it's not char and varchar, it's, how is it called?
Blobs, isn't it?
It's blobs, yeah. I just can't remember the type when we have binary, right? Is it binary, var binary? I think it's binary, var binary. And these get aggregated to, exactly, so that's the one, binary, var binary. There might be limited number of bytes. And the output of the aggregation of that, when you concatenate them, would be byte A. Basically the blob type that's called byte A in PostgreSQL. So The answer is really look up the documentation, and the documentation will tell you for every aggregation function what is going to be the data type that is output by it, right? Which might not be the same one as the original column. Any other questions? Don't see in the room. Any other questions on Zoom? Okay, we can take all the time for questions. This is what we are here for. So as a reminder, these are the possibilities. So I told you inner join, left outer join, right outer join, full outer join, but you don't need to actually say inner or outer because it's implicit. If you say left, right, or full, PostgreSQL will know that you mean outer because there is no such thing as a left inner join that doesn't exist. So if you're lazy, you can just omit the outer. And if you don't specify left, right, or full, you also don't need to say inner because PostgreSQL will know what you mean. It knows you mean inner. And if you don't say anything, that's a cross join. But again, a cross join is not really a join. It's really just a Cartesian product. Okay, I think that's enough for today, right? We've seen the sorting, order by, the aggregation with group by, the joining of tables with all the kinds of join with on, using, and natural. So you've done a great job of following what I've been telling you. I strongly recommend that you read the chapters of the book on the library, and I strongly recommend that you get your hands onto a Jupyter notebook and write all the queries you can write to make yourself familiar with all of that. There is no secret, it's the practice. Do it, write all the queries you can. This is how you're going to get familiar with PostgreSQL. When you have your Jupyter notebook, you can just write any queries you want, so you can explore and play and see what happens. And again, I repeat, on exam day, you will have the documentation. We make it accessible, so you can look it up. All right, so I think that they are making a lot of noise outside. Probably they want us to go. So I wish you to enjoy your meal and enjoy the exercise session this afternoon. And I'll see you next week at 10 a.m. for the next course. Thank you.